It would be a code violation to double-barrel the secondary lines of the transformer and feed two different 200-amp panels. According to the 2020 National Electrical Code, specifically Section 450.3b, the secondary conductors of a transformer must be protected by a single overcurrent device on the primary side. In the scenario described, the primary side of the transformer is protected by a 150-amp breaker. Therefore, the secondary conductors can only be rated for a maximum of 150 amps. Since the two 200-amp panels will each be drawing more than 150 amps, double-barreling the secondary lines of the transformer would violate the code. Let's delve into the specifics of why this is a violation and how to properly protect the transformer and downstream panels. Firstly, understanding the purpose of overcurrent protection is crucial. Overcurrent devices, such as circuit breakers and fuses, are designed to protect electrical equipment and conductors from excessive current that could cause overheating, damage, or even fire. The National Electrical Code provides guidelines for sizing these overcurrent devices to ensure safety and prevent damage. Secondly, NEC Section 450.3 addresses the overcurrent protection requirements for transformers. This section outlines the rules for protecting both the primary and secondary sides of a transformer. Specifically, Section 450.3b focuses on the secondary side protection for transformers rated over 600 volts, nominal. In this situation, the 480 volt to 120/208 volt transformer falls under this category since the primary is rated over 600 volts, nominal. The code dictates that the secondary conductors must be protected by an overcurrent device rated or set at not more than 125% of the transformer's secondary current rating. However, an exception allows for the primary overcurrent device to serve as protection for the secondary conductors, provided certain conditions are met. To elaborate, when relying on the primary overcurrent device for secondary protection, the primary overcurrent device must be sized appropriately to protect the secondary conductors. In this scenario, the primary is protected by a 150-amp breaker. This means the secondary conductors are effectively protected up to a maximum of 150 amps. If the secondary conductors were to carry more than 150 amps, the primary breaker would trip, preventing damage to the transformer and conductors. Now, considering the proposed installation with two 200-amp panels fed from the transformer's secondary, it becomes clear why double-barreling the conductors would be a violation. Each 200-amp panel is capable of drawing up to 200 amps. If both panels were to draw their maximum current simultaneously, the total current flowing through the secondary conductors would be 400 amps. This far exceeds the 150-amp protection provided by the primary breaker. The double-barreling of the conductors does not change the overcurrent protection limits imposed by the primary breaker. Even if the conductors themselves are rated to carry 400 amps, the weakest link in the system is the 150-amp primary breaker. If an overload or short circuit occurs on the secondary side, the 150-amp breaker will trip, but only after the secondary conductors have been subjected to a current far exceeding their protected limit. This could result in overheating, insulation damage, or even a fire. To comply with the NEC, several alternative solutions can be implemented. One solution is to install a single main breaker on the secondary side of the transformer, sized appropriately to protect the secondary conductors. This breaker would need to be rated at 150 amps or less to comply with NEC Section 450.3b, given the 150 amp primary protection. The two 200-amp panels could then be fed from this main breaker, with each panel having its own 200-amp breaker for individual circuit protection. However, the total load connected to the two panels must not exceed the 150-amp capacity of the main breaker. Another option is to use a larger transformer with a higher secondary current rating. If a larger transformer is installed, the primary breaker can be upsized accordingly, and the secondary conductors can be sized to match the new transformer's capacity. In this case, if the intention is to feed two 200-amp panels, a transformer with a secondary current rating of at least 400 amps would be required. The primary breaker would then need to be sized to protect the larger transformer's primary windings. A third option is to re-evaluate the loads connected to the two 200-amp panels and determine if the total load is truly necessary. It may be possible to reduce the size of the panels or redistribute the loads to other existing panels. While reducing the overall demand on the transformer, it may be possible to comply with the NEC without having to install a larger transformer or additional overcurrent protection. When selecting the appropriate solution, it is essential to consider the specific application and the total load requirements. A qualified electrical engineer or contractor should be consulted to ensure that the installation complies with all applicable codes and standards. In addition to the NEC requirements, it is important to follow all manufacturers' instructions and recommendations for the transformer and associated equipment. Proper installation and maintenance are crucial for ensuring the safe and reliable operation of the electrical system. Let's consider a few examples to further illustrate the concept. Firstly, assume the 480 volt to 120/208 volt transformer has a nameplate rating of 75 kilovolt amps. To calculate the full load secondary current, we would use the following formula: transformer kilovolt amp rating times 1000 divided by the square root of 3 times the secondary voltage. Therefore, 75 times 1000 divided by the square root of 3 times 208 equals approximately 208 amps. Based on NEC section 450.3b, the secondary overcurrent protection should not exceed 125% of the transformer's rated secondary current. In this case, 125% of 208 amps is 260 amps. However, since the primary is protected by a 150 amp breaker, the secondary conductors are effectively limited to 150 amps. Therefore, installing a single 200 amp breaker on the secondary side would be a violation. Secondly, imagine the transformer has a nameplate rating of 150 kilovolt amps. Using the same formula, the full load secondary current would be 150 times 1000 divided by the square root of 3 times 208, which equals approximately 416 amps. In this scenario, 125% of 416 amps is 520 amps. If the primary breaker is upsized to protect the transformer's primary windings, a secondary breaker rated at 400 amps could be installed. This would allow for the two 200 amp panels to be fed from the secondary side, provided the total load does not exceed 400 amps. In conclusion, double barreling the secondary lines of the transformer to feed two different 200 amp panels would be a code violation because the primary overcurrent protection limits the secondary current to 150 amps. To comply with the NEC, one must either install a single main breaker on the secondary side, use a larger transformer with a higher secondary current rating, or re-evaluate the loads connected to the panels. Always consult a qualified electrical engineer or contractor to ensure compliance with all applicable codes and standards. Proper overcurrent protection is essential for ensuring the safe and reliable operation of the electrical system. By adhering to the NEC guidelines and following manufacturers' recommendations, one can prevent damage to equipment, protect personnel from electrical hazards, and maintain a safe and compliant electrical installation. The principles discussed here are applicable to a wide range of electrical installations, not just transformers. Understanding the purpose of overcurrent protection and the requirements of the NEC is crucial for anyone involved in the design, installation, or maintenance of electrical systems. By staying informed and following best practices, one can contribute to a safer and more reliable electrical environment. Let's elaborate further on the practical implications of violating the code and the potential consequences of double barreling the secondary conductors. One of the most significant risks is the potential for overheating and fire. If the secondary conductors are subjected to a current exceeding their capacity, the conductors will begin to heat up. This heat can damage the insulation surrounding the conductors, leading to short circuits and ground faults. In extreme cases, the heat can ignite nearby combustible materials, resulting in a fire. Another risk is damage to the transformer itself. If the secondary conductors are overloaded, the transformer's windings can overheat, leading to insulation breakdown and eventual failure. Replacing a transformer can be a costly and time-consuming process, so it's essential to protect it from overload conditions. In addition to the physical risks, there are also legal and financial consequences to consider. If an electrical installation is found to be in violation of the NEC, the building owner may be subject to fines and penalties. Furthermore, if a fire or other incident occurs as a result of a code violation, the building owner may be held liable for damages and injuries. Insurance companies may also deny coverage for claims resulting from code violations. Therefore, it's crucial to ensure that all electrical installations comply with the NEC and other applicable codes and standards. To further clarify the concept of overcurrent protection, let's discuss the different types of overcurrent devices and their characteristics. The two most common types of overcurrent devices are circuit breakers and fuses. Circuit breakers are electromechanical devices that automatically interrupt the flow of current when an overload or short circuit is detected. Circuit breakers can be reset after they trip, making them a convenient and reusable option. Fuses, on the other hand, are one-time use devices that melt and break the circuit when an overcurrent occurs. Fuses are generally less expensive than circuit breakers, but they must be replaced after they blow. Both circuit breakers and fuses are available in a variety of sizes and types, each designed for specific applications. It's essential to select the appropriate overcurrent device for the specific circuit and load requirements. In addition to circuit breakers and fuses, there are also other types of overcurrent devices, such as motor overload relays and ground fault circuit interrupters. Motor overload relays are designed to protect electric motors from overheating due to overload conditions. Ground fault circuit interrupters are designed to protect personnel from electric shock by detecting and interrupting ground faults. When designing an electrical system, it's crucial to consider all potential overcurrent conditions and select the appropriate overcurrent devices to protect equipment and personnel. The NEC provides detailed guidelines for selecting and installing overcurrent devices. It's essential to follow these guidelines to ensure the safe and reliable operation of the electrical system. The selection of overcurrent protection is also related to the conductor ampacity. Conductors are selected and sized based on the load and the overcurrent protection that is in place. For example, you cannot install a 20 amp breaker on a 14 American wire gauge copper wire. The purpose of conductor ampacity is to ensure that the wires are not being overloaded and causing a fire. A 14 American wire gauge copper wire is typically rated for 15 amps, but this depends on the installation method, ambient temperature and other factors. If you install the wrong size breaker, you can cause damage to the wire. In summary, double barreling the secondary lines of the transformer and feeding two different 200 amp panels is a code violation that can lead to serious consequences. To comply with the NEC, you must either install a single main breaker on the secondary side, use a larger transformer with a higher secondary current rating, or re-evaluate the loads connected to the panels. Always consult a qualified electrical engineer or contractor to ensure compliance with all applicable codes and standards, and remember the goal is safety for people and equipment.